The Aufbau Principle says that as I add protons to build up the elements, I similarly add electrons to build up the elements, and these electrons get added into the orbitals that I've been able to get. 1s, 2s, 3s, 3p, d, f, all of these different orbitals. So here is how I would use this principle going down the periodic table. I start with hydrogen, I have a proton, and I have one electron, so I put that in the 1s orbital. So the electron configuration of this is 1s1. Go down to helium, I add another proton, add another electron. So the electron configuration of this is 1s2. I add 2 electrons for every one of my individual orbitals. My p orbitals have 3 individual orbitals, so in each one of those will go 2. For my s, I only have 1, so for each one of those, I get 2 as well. So now I go past helium. I add an electron in with the opposite spin. That's why it's pointed down. The spin's really not so important right now. I'm just doing it just because that's just the way I'm going to do it. But just don't really think about the electron spin for right now. It's just not really that important, to be honest. So I'm putting the spins in properly, but I didn't really care to discuss them. So next I go to lithium. My 1s orbital is filled, so then I go to my next highest energy orbital, which is 2s. So I add that electron in there. Next is beryllium. Same process. My 1s1 is already filled. Now I add that one to my 2s. So for boron, I finally get to a different type of orbital. My previous orbitals are filled. I have 1s, 1s2, 2s2, and now I have 2p1. So I add this into the p orbital. Next I get to carbon, and now I have a decision to make. Do I continue to add them to the same orbital, or do I add them to different orbitals? And the answer is to add them to different orbitals. And if we just think about it logically, electrons have the same charge. So they're going to want to spread themselves out as much as possible. If there's already an electron in an orbital and there's an empty orbital, more than likely it's going to go to the empty orbital because it wants to be away from the same like charge because they repel each other. So that's why they go into different orbitals. So carbon, it adds to the p orbital, but it adds into a different p orbital. It doesn't go into this same one. So as I continue, nitrogen, same thing, goes into a different orbital, and then now I've run out of empty orbitals, and as I continue adding, now they will be forced to share orbitals. I have no choice. So I continue adding all the way until I get to neon, and then I have a full s orbital and p orbital. And here is a good time to talk about the idea of the octet. The octet is talking about the valence electron configuration. Now the valence electron configuration is the electron configuration of the outermost electrons. So notice how after I filled up this 1s orbital here, it really became quite irrelevant. It was just filled. And then I started filling the outer shells, the 2s and 2p. These would be considered the valence electrons for boron on. Well, technically for lithium on, but just don't worry about it. I guess boron's a weird element. But for carbon, we talk about the 8 outer electrons. So these would be the valence electrons. These would be the valence electrons for all of them. And they're the valence electrons because they share the same energy level, 2s and 2p. So they are the outermost electrons for these elements. So from now on, I'm only going to mention basically the valence electrons. I don't really care so much about these electrons. These are going to be called the inner core electrons, and since they're on the inside, these outside electrons are basically going to shield these inner electrons if I think of it from an outside perspective. So I can't really get to these electrons easily, so if a reaction is going to take place, it's going to use these outer electrons. So that's why I care about the valence electrons and not so much about the inner electrons. So from now on, I'm just going to write 3s2, 3p6, and just mention the valence electrons. I'm just going to assume these are all filled on the innermost electrons. And I guess I want to mention one more thing, which is going to lead into bonding and about why we care about valence electrons and the octet and the outer electron configuration. And again, it has to do with bonding, because these elements, especially the nonmetals with the s and p orbitals, they're going to want to get 8 electrons in the outer shell, and what it does is it makes it more stable. So often, if I think back to earlier where I was doing chemical reactions where I saw like sodium plus 1, things like that, what sodium plus 1 is this sodium minus an electron. So sodium, if this were to lose an electron, it would have the electron configuration of neon, and neon has 8 electrons in its outer shell, which means it has an octet, has 8 electrons in the outer shell, and it's in its most stable electron configuration. Fluorine often will bond with one other element, and if it shares an electron with something else, and it gets another electron here, then it will also have a neon electron configuration. Or often fluorine will just simply be an ion. It will be fluorine minus 1, which means it has an extra electron, and therefore a neon electron configuration. So a lot of this stuff that I'm learning here really has to do with just looking at electron configurations and knowing what these electron configurations are. It will help me understand bonding more. It'll help me understand what is trying to happen. A lot of these non-metal elements, oxygen needs 2 more electrons. So generally it tends to undergo 2 bonds, or a single double bond, which is basically 2 bonds. If I think of water, H2O, it's bonded to 2 hydrogens. And if they were to share electrons, then oxygen would get these 2 electrons, and it would have 8 all of a sudden. If I go back to hydrogen, it will get another electron as well if it was to share with oxygen, and then it has, in this case, I guess they call it a duet, because it doesn't have enough electrons to fill up these shells. So when hydrogen is in its most stable configuration, it has this electron configuration. But that's the idea, really. Or carbon, it will generally undergo 4 bonds. So if I were to add 4 electrons here, 1, 2, 3, 4, now it has an octet. So you can see the idea of where this is leading to. It's going to lead to bonding. What are we trying to do? Get a full valence shell. So that is that. And I will go a little bit further into the transition metals. So this process is going to continue predictably. I'm going to do exactly the same thing for sodium all the way to argon. I'm going to just add electrons. Nothing special happens. I get to argon. 3s2, 3p, fine. Now what's going to happen is, ordinarily I would think that from 3s, 3p, next would come 3d. But in fact this is not the case. Before I get into the 3d, 4s is filled. Now why that happens is because the way the electron's energy is in the 4s shell, it's able to penetrate. See, look, by this time I've got a lot of inner core electrons. I've got the 1s shell, the 2s shell, the 2p shell, the 3s shell, and the 3p shell filled. Now the shape of the orbitals, it's easier for the 4s electrons to penetrate these other orbitals and get closer to the nucleus just by its shape. At least that's what they say. And the 3D, because of the shapes of those orbitals, it has a harder time getting closer to the nucleus, so therefore the 3D is in fact a higher energy than the 4s, even though 3D you would think would come first, but it doesn't. And it can be verified using different experiments are also chemical properties. Sodium has very similar properties to potassium because it has the same type of electron configuration. It wants to get rid of this one electron and get an argon configuration, or this noble gas, or octet. And if anyone's ever thrown potassium in water, it reacts explosively to get rid of those electrons. And I'm sure plenty of people have seen in probably biology or in biochemistry, well, probably not biochemistry at this point since we'd be learning general chemistry, but you'll notice that potassium almost always has a +1 charge. That's because it gets rid of that electron as soon as it can to get this configuration. So the 4s gets filled before the 3d because it can penetrate the other electrons better than... It can penetrate the shielding of the other electrons. See, the other electrons, if I think this nucleus, here are a bunch of electron clouds. The 4s will have an easier time penetrating these other electrons to get a little bit closer to the positive nucleus, so it's lower energy. So anyways, a 4s gets filled. So I got potassium, and then I get calcium. Then after this, now the 3d gets filled. So I start on scandium, and right now I'm only just going to be talking about the outer electrons. I don't really care about the core electrons. So I start with scandium. It's going to proceed normally, but there are going to be a couple of things that happen here that one would not expect. So we'll just go through it. Scandium, it's normal. I just start adding into the d orbital, 4s2, 3d1. Then I get titanium, same thing, 4s2, 3d2, just add another electron in. Then I get to vanadium. It's still going according to plan. I have my 4s orbital filled, and then my 3d is added another electron. It's not until I get to chromium where something unexpected takes place. I add another electron to my 3d orbital, but then one of the electrons from the 4s orbital goes into the 3d orbital to give this electron configuration where there is one electron in each orbital, and I have no idea what causes this. I have no clue what causes this, but apparently it's been experimentally verified that this is indeed what happens. So this is one of the, well, there are two unexpected events. This is one of them. So chromium, one of the 4s ones goes into the d orbitals, and then I have one in each. It's just, obviously this configuration is just more stable than having just one electron missing from the 3d orbital. But then once I get to manganese, it continues normally as well. I just add another electron to my 4s orbital. It's the lowest energy, so that's where it would be added. Then I go to iron, and it continues normally. Iron, cobalt, nickel, still operating normally. And it's not until I get to copper where another strange thing happens. Instead of getting just another electron here, an electron goes into the d orbital, and then again this electron from the 4s orbital goes to the 3d orbital to give me a full d orbital. And again, I'm not really sure what causes it. It must just be more stable. I mean, that's the only reasonable explanation for it. But why is it? I'm not sure. And then finally I get to zinc, and then zinc is exactly what I would think it would be. It's just everything filled. So one thing to know is about the transition metals. And these kind of switches that it does is that these have big versatility and stabilities. Obviously, this is a stable electron configuration, this is a stable electron configuration, and so are the top and bottom ones. But what I mean is, normally when I see transition metals, those are the kinds of elements where I'll get like a +7 or a +5 or -5. If I remember from oxidation reduction reactions, they are very versatile in what their electron configurations can be. They can have many different charges, and it's probably due to these kind of in-between stabilities that can be had along the way, where there's one in each orbital, where the orbitals are full, where the whole d orbital is full. So now one can see why there are so many charges possible, is just because it has more orbitals, whereas potassium and some of the non-metals, normally I'll only see generally like a -1 or a +1, or maybe even a +2, like for magnesium or something like that, or calcium, or a -2 every now and then. But generally I don't see like a -5, +5, +7. I think manganese I've seen like +7s sometimes, or maybe it was +5. But anyways, chromium I've definitely seen a +7. So they can get rid of and accept quite a lot of electrons, and if you look at all of these orbitals, you can see why. And then the periodic table continues normally. These sort of jumps will happen again once I get to the 4d orbital. Also, the 5s orbital will come before the 4d orbital. That will continue to happen. And if I look at the periodic table, this is how it's set up. The S is on the left, the P is on the right, the D is in the middle, and then the F I'm not even going to talk about. All kinds of weird things happen where it skips, goes into Ds, and the Fs are empty. The D and the F orbitals often have similar energies, so you get a lot of strange things happening, but all of those elements are very rare, and I guess the only real time you'd run into them is if you're like a nuclear physicist or something like that. They're just ignore them. Really what we're going to focus on most of the time is just the non-metal ones, because they're related to organic chemistry and they're the most common elements, since they're made in fusion of stars, where these other elements require like neutron stars or some other explosion, something else. They're not common at all. So normally we're going to be dealing with octets. Obviously, when I'm dealing with transition metals, the octet rule is not really going to apply, because they have different orbitals. The reason the octet rule is so important, because most of the elements that we deal with around here, carbon, nitrogen, oxygen, their valence shell has 8, or can have up to 8, and they're going to try to get 8 electrons. So that is going to be the main focus of what the bonds that are going to be taking place coming up are going to be about. It's going to be about a lot about oxygen, nitrogen, fluorine, carbon, trying to get 8 electrons. And these transition metals, we're not really going to see them so much anymore. At least as far as bonding is concerned, there might be a couple examples just to show, but really not really going to be talking about too much until someone starts learning more about inorganic chemistry. But this material really doesn't go into it that much. But it's there just so you know, and these are very interesting things. So these are kind of there just as like a preview in case you would have some kind of interest in this. Then you would know about it and you say, well, I'm interested in learning what more of these transition metals seem quite interesting, and they are. But as for the purposes of the continuing information of this class, I really wouldn't spend any time learning about this kind of stuff. Spend all the time learning about these kind of elements: carbon, nitrogen, oxygen,